I want to start today with a question that feels a bit like a trap, so just bear with me for a second.
All right.
If I hold this pen up right here and I just let go of it, it falls to the table. Why?
Well, the classical answer, the one we've all been trained to give since we were 5 years old, is gravity. The Earth has mass, and that mass creates a force, and that force reaches out like a muscle and just drags the pin down.
Right. And that's the Newtonian view. It's totally intuitive. It's comforting, honestly. But what if I told you that is fundamentally and structurally wrong? What if I told you that gravity isn't a force that pulls things at all, but rather it's a habit of space itself, like a structural necessity?
It's a pretty bold way to open a deep dive, but you're absolutely right. We are entering some very, very deep waters today.
We really are. We're looking at a stack of papers that suggest the universe isn't built by forces pushing particles around like billiard balls.
Yeah.
Instead, it's sculpted. It's carved out of a block of possibilities. And what we actually see, the galaxies, the atoms, you, me, is just the stuff that survived the chisel.
That is a beautiful, if slightly terrifying image. And we are looking at the work of researchers Shrikant Bhosale today.
Yes, specifically a series of papers published just this month in February 2026. He's associated with twistpool.com and the Government Medical College Sampaji Nagar. And I have to say, when I first saw the titles of these papers, things like Constraint Geometry and The Structural Necessity of Attractive Gravity, I really thought we were in for a dry math lecture.
Yeah, they don't exactly sound like beach reads.
Not at all. I was ready for equations that would just make my eyes completely glaze over. But then right in the middle of all the high-level physics, I started reading about 17th century Indian aqueducts.
And that is the twist that really hooks you in. It's not every day you see a unified field theory that relies on the hydraulic engineering of the Mughal era.
Exactly. And suddenly I realized I wasn't reading a standard physics paper, I was reading a detective story. A story that literally connects an ancient water system in Aurangabad to the spin of distant galaxies. And somehow it all hinges on the idea that geometry is the boss.
Geometry governs energy before equations do. That's the core thesis here. It's a very Penrose-esque way of looking at the world.
So our mission for this deep dive today is to take this journey across all these different scales. We're going to go from the underground tunnels of the Nahar-e-Ambari aqueduct all the way to the edges of the universe where dark matter is supposed to be hiding.
Yeah, quite a trip.
It is. And along the way, we're going to see if Bhosale's theory of constraint geometry can actually unify gravity and electromagnetism, which is kind of the holy grail, right?
It absolutely is.
Yeah.
And perhaps most importantly, we need to address the operational aspect of this. Because this isn't just theory. Bhosale is actually proposing a way to test this. He's operationalizing the math into a physical machine.
Which is wild to me. Usually these grand theories end with a vague statement like, and in 100 years, maybe we can test this. But he's talking about a tabletop experiment.
Which makes it high stakes.
Yeah.
It's entirely falsifiable. If the experiment fails, the theory fails.
Okay, let's unpack this. We need to start at the bedrock. The theory is called constraint geometry. What does that actually mean? Because when I hear the word constraint, I think of handcuffs or rules or just limitations.
That's actually a really good place to start. To understand this, you have to unlearn the Lego model of the universe.
The Lego model.
Yeah, think about how we usually teach physics to, high schoolers. We say, here is a particle, like a little Lego brick, and here's another particle. We snap them together using a force, and that force is the glue or the studs on the top of the block.
Right, you just keep adding pieces.
Exactly. You keep adding pieces until you have a proton, then an atom, molecule, a table, a planet. Structure is additive. You build up from the very bottom.
Sure. Big things are made of small things stuck together. That's basically the reductionist view we all rely on.
But Bhosale's paper, the one titled Constraint Geometry in the Information Scaling Law, flips that entirely on its head. He argues for what he calls a selection principle. He says physical structure, essentially reality itself, isn't what you build. Reality is what remains after you filter out the impossible.
Okay, hold on. That sounds very poetic, but what does it actually mean physically, filtering out the impossible?
Think of the sculptor analogy you used earlier. If you want to make a statue of a horse, you don't take a pile of clay and stick it together until it looks like a horse. That's the force method, the Lego method.
Right.
Instead, you take a solid block of marble. And theoretically, that block contains infinite possible shapes inside it. It contains a horse, a bird, a perfect cube, a messy pile of dust.
You just chip away everything that isn't a horse.
Exactly. The horse isn't built, it is revealed. In this constraint framework, the laws of physics are the chisel. They are the geometric constraints. Bhosale talks a lot about illegal geometric intersection.
Illegal intersections, that sounds like a traffic violation.
In a way, it kind of is.
Hmm.
Imagine two solid steel balls. If you try to push them directly through each other, they just bounce off. They cannot occupy the exact same space at the exact same time.
Because they're solid.
Right. That is a geometric constraint. The universe says this configuration is illegal. You cannot proceed.
Okay, I follow that. Two things can't be in the exact same place. It's basic physics.
But Bhosale is taking that simple, everyday idea and scaling it all the way down to the very fabric of space-time itself. He suggests that the particles and the forces we see, things like electrons, gravity, light, are just the shapes that survive the filter.
They're the horse and the marble.
Yes, they are the kernels that actually fit the puzzle. The universe is constantly shifting, constantly trying to minimize these illegal intersections.
So we are being pushed around by invisible forces. We are just sliding into the only available slots in the geometry.
Precisely. The paper describes this process as a variational minimization of geometric errors. The universe is basically constantly trying to solve a massive Sudoku puzzle. It's arranging itself to minimize any conflict.
And when it finds a solution...
When it finds a stable solution, you get the stable structures we see. The proton.
Yeah.
The electron. They are the solutions to that geometric puzzle. They're the configurations where the error is practically minimized to zero.
I have to say, this sounds incredibly elegant. It feels very clean. But my skepticism meter is definitely flashing right now. You can say the universe is a sculptor all day, but physics runs on numbers. You can't calculate the orbit of Mars with a metaphor about a block of marble. You need hard data.
And that is exactly where this gets weirdly specific. And this is why I think these papers are getting so much attention.
Yeah.
Because when you run this sculpting logic, mathematically, when you actually calculate what kind of geometric kernel can close on itself without any errors, specific numbers pop out.
These are the magic numbers that were mentioned in the outline.
Magic numbers. The paper derives a geometric invariant called phi, and that equals exactly 120. And another one, eta, which is exactly 9.
120 and 9. Those just sound like random integers. Why those specific numbers?
They relate directly to the degrees of freedom and the dimensionality of the geometric kernel he's describing. But you're right, on their own, they are just numbers. However, if you combine them within this constraint framework, you can mathematically derive the fine structure constant.
Okay, we need to pause on the fine structure constant because I see this number pop up in sci-fi and pop physics articles all the time. It's 1 over 137, right? Why is everyone so obsessed with this specific number?
Because it is quite literally the number that allows us to exist. It governs the exact strength of the electromagnetic force. It dictates how tightly an electron holds onto a proton.
It dictates the speed of an electron in an atom too, right?
Yes, specifically in the first orbital of a hydrogen atom. So it's basically the strength of the glue that holds all atoms together.
So it's a big deal.
It's a huge deal. If that number were even slightly different, say it was 1 over 138 or 1 over 1 or 30 instead of 137 stars, wouldn't burn the way they do. Carbon wouldn't bond to form complex chains. Chemistry, as we know it, would completely collapse.
Life would be literally impossible.
Entirely impossible.
And usually in physics, where do scientists actually get this number from? Do they derive it from some master equation like E equals mc squared?
No. And that is the great embarrassment of modern physics. Richard Feynman, the Nobel laureate, famously called it one of the greatest damn mysteries of physics. He basically said, we just have to write it on the blackboard and accept it.
We just accept it. That doesn't sound very scientific.
Well, we measure it. We put a highly sensitive sensor in a vacuum chamber, run an experiment, and say, okay, the dial reads approximately 1 over 137. It's an empirical fact. We know it's true, but we have absolutely no idea why it is that exact value.
It's just a random setting on the universe's dashboard.
Exactly. In the standard model of particle physics, you just have to type that number in manually to make the math work. But Bhosale is claiming he didn't measure it, he derived it.
That is a massive claim to make.
He gets an alpha value of approximately 1 over 137, not by looking at atoms under a microscope, but by looking purely at the geometry of this abstract kernel. He says it's a mathematical necessity.
So it's derived from the way the geometry has to close on itself to avoid those illegal intersections we talked about.
Yes, it's a purely axiom-driven approach. He's deriving the fundamental constants of nature from pure shape. If this holds up, it removes the arbitrariness of the universe. It means reality is a geometric inevitability.
That is genuinely mind-bending. But, as we said earlier, math can be a bit of a fantasy land sometimes. You can make numbers do pretty much anything on a piece of paper if you twist them hard enough.
You can?
So how do we know this actually connects to the real messy physical world of dirt and water and gravity?
That is the perfect transition to the second part of our deep dive. Because Bhosale absolutely does not stay in the abstract high-dimensional math, he takes us directly to 17th century India,
To the aqueduct.
to the Nahar-e-Ambari aqueduct.
I actually spent some time reading about this after looking at the papers. It was built between 1612 and 1617 by a guy named Malik-Ambar in Aurangabad.
Malik-Ambar is a truly fascinating historical figure in his own right. He was an Ethiopian slave who rose to become a regent and a brilliant military genius in the Deccan region. He was constantly fighting off the Mughal Empire, and to do that he needed serious infrastructure.
But why is a cutting-edge 2026 physics paper citing a 400-year-old water tunnel?
Because Malik-Ambar practically solved a physics problem that we are just now fully appreciating in modern terms. He built a 16-kilometer water network that has absolutely no pumps.
No electricity, no external energy source at all.
None. It operates entirely on gravity.
But wait, now, it uses gravity, but it uses it in a very specific way, right? Because if you just dig a ditch for 16 kilometers and let water slide down, what happens?
Well, if the slope is too steep, the water flows too fast, it splashes everywhere, it erodes the banks, it gets messy.
It becomes turbulent.
Right. It wastes all its energy in noise and heat and erosion. But on the other hand, if the slope is too flat, the water just stops. It stagnates and goes nowhere.
So there's a sweet spot.
Malik-Ambar found the exact geometric sweet spot. The system creates what the paper calls potential energy transduction. It uses incredibly precise gradients and siphons, which the builders called bomba, and these specialized access shafts called abgir-nali.
And the whole point of this architecture is to keep the flow laminar.
Laminar. Smooth. Think of honey pouring off a spoon versus white water rushing over rocks in a river. The paper argues that because the geometry of the aqueduct is so strictly constrained, I mean, we're talking tiny slopes and huge precision over kilometers, the system operates in a regime where it actively recovers configurational energy.
Configurational energy, is that a standard physics term?
It's used in this context to describe the energy inherent in the physical order of the system itself. Because the water isn't fighting against itself in chaotic swirls, it retains its potential energy much further than standard friction calculations would ever predict.
So the tunnel itself, the physical shape of the tunnel, is acting like a battery, preserving the energy of the water.
Exactly. And the paper introduces a metric to quantify this. It's called the geometric Reynolds number, or Re sub G.
I actually know the regular Reynolds number from basic fluid dynamics. It basically tells you if a fluid is flowing smoothly or if it's turbulent and chaotic.
This is the pure geometric version of that.
Yeah.
It's defined mathematically as the clearance distance divided by the transition length.
Okay, you don't need to memorize the formula if you're listening, but just break those terms down for us. What do clearance and transition actually mean here?
Clearance is simply the gap. It's the physical space available for the flow. Transition is the distance over which the geometry of the container changes.
So if you change the shape of the tunnel too abruptly, you create a bottleneck, and that causes turbulence.
Right. And if you give the water too much room to wiggle around you, you also create turbulence. You have to keep the clearance tight, and you have to keep the transitions long and incredibly smooth.
And what's the final verdict on this 17th century aqueduct?
The Nahar-e-Ambari operates at a geometric Reynolds number of consistently less than 1. That is deep in the laminar regime. It is highly efficient, sustainable, and self-reinforcing.
And if it goes wrong?
If the Re sub G goes above 10, you hit the turbulent regime. Total chaos, massive energy dissipation, the system fails.
So Malik-Ambar, over 400 years ago, intuitively understood this geometric Reynolds number concept.
He fundamentally understood that if you constrain the geometry of the flow precisely enough, you create a self-sustaining system. He obviously didn't have the modern algebraic equation, but he had the geometry-first intuition. He was doing applied relativity with water.
That is just incredible. But Bhosale is saying we can use this exact same principle today, right? But to do what? Because we have electric pumps now. We don't really need to build aqueducts like that anymore.
We might not need them for moving water, but we might absolutely need them for energy generation. And this is where the proposed Amber engine comes into play.
This is the laboratory experiment proposed in the papers.
Right. He's proposing a physical lab experiment, a tabletop device. At its core, it's just a torsion pendulum.
Okay, so for anyone listening, picture a weight hanging on a wire, just twisting back and forth.
Simple enough. But here is the massive innovation. You surround that hanging pendulum with a helical cage, a rigid structural boundary shaped like a corkscrew that completely surrounds the path of the swinging weight.
Does the pendulum hit the cage as it swings?
No. That is the most critical point of the entire setup. It must not touch. It relies entirely on clearance, just like the water in the aqueduct doesn't violently scrape against the ceiling.
Wait, so the cage is basically playing the I'm not touching you game, but it's still somehow affecting the pendulum.
Yes, it physically constrains the field around it. It actively limits the illegal intersections in the vacuum or the air directly around the weight. By interacting with the strict geometric constraints of that cage, the pendulum is forced into that laminar regime we talked about.
And re sub g of less than 1?
Exactly.
And what is the actual result supposed to be?
The hypothesis is that you will measure a transient efficiency gain. The pendulum will literally swing longer or more efficiently than it mathematically should, according to standard classical damping models. The paper actively predicts a measurable gain of about 10 to 30%.
10 to 30%. That's not a rounding error. That's a massive chunk of energy.
It really is. It would be unmistakable in a lab setting.
But wait, an efficiency gain. Are we talking about free energy here? Because if we are talking about a perpetual motion machine, we probably need to end the deep dive right now.
No, no. And the rigorous expert in me has to be very, very clear about this. The paper is extremely careful about adhering to the strict laws of thermodynamics. It is absolutely not creating new energy from nothing.
Then where is this extra 30% coming from?
It comes from pure recovery. In a normal swinging pendulum, energy is constantly being lost to microturbulence. Tiny chaotic movements in the surrounding air or even friction deep in the molecular lattice of the wire itself.
And that energy just turns into ambient heat and is lost forever.
It's total waste. But the Ambari engine claims that by imposing this strict helical geometric constraint, you actively suppress that microturbulence. You force the energy to remain laminar.
So you are basically harvesting the order of the system. You aren't creating new energy. You're just stopping the system from bleeding its existing energy so fast.
Exactly. Think of it like putting a highly streamlined aerodynamic shell on a race car. You aren't magically creating more gasoline in the tank, but you are making the car go much further because you're fighting the wind resistance less.
I see. But here you aren't streamlining the physical car. You're somehow streamlining the actual space the car moves through by using the helical cage.
That is a perfect way to phrase it. It is a fascinating concept. He is operationalizing the historical lesson of the Mogul aqueduct inside a modern, high-tech physics lab.
And there's philosophical supplement attached to the paper that links all of this back to Sir Roger Penrose Wright.
Yes, the Nobel Prize winner. Penrose has maintained this deeply held view that geometry governs energy before equations do. He genuinely believes geometry is the foundational layer of reality.
So Bhosale is essentially saying Nahar-e-Ambari proved Penrose right in 1612, and now we can mathematically prove it again today with the Ambari engine.
That is the bridge he's building, from an ancient military engineer to a modern physicist to a Nobel laureate.
That is a fantastic bridge. But here's where I really want to push you a bit. We've been talking about flowing water and swinging pendulums, and that's all very terrestrial. It's stuff we can touch. How do we leap from a water tunnel to dark matter? Because the title of this episode promised me the geometry of reality and distant galaxies.
And we shall deliver on that promise. This is the true aha moment of the entire theory. The source paper titled Operationalizing the Randall-Sundrum Geometric Intuition takes this terrestrial concept of flow and applies it directly to gravity itself.
Okay, set the cosmic scene for us here. What exactly is the major problem with our understanding of gravity right now? Why do we even need a new theory?
The biggest problem is the galaxies. They simply spin way too fast.
Too fast.
Yes, based on all the visible matter we can measure the stars. The dust galaxies, fundamentally should not have enough gravitational pull to hold themselves together at the tremendous speeds they're spinning. They should physically fly apart.
It's like a playground merry-go-round spinning so fast that the kids just get violently thrown off into the dirt.
That's a great analogy. So to fix this glaring hole in the math, scientists basically invented dark matter. They hypothesized this invisible stuff that adds a massive amount of extra gravity to hold the kids safely on the ride.
Right. It's essentially a mathematical band-aid. We can't see it, we can't touch it, but we all agree it simply must be there to make the equations balance. Roughly 85% of all the matter in the universe is supposed to be made of this dark stuff.
But recently, there is a massive new problem with that band-aid.
And what's that?
It involves a very specific rare type of galaxy called an ultra-diffuse galaxy, or UDG.
UDGs. I've seen these referred to as ghost galaxies in the news.
Yes. They are incredibly large physically, but very, very faint because they have so few stars. And recently, astronomers observing them have found a stark bifurcation, a severe split in the data.
What kind of split are we talking about?
Well, some of these ghostly UDGs seem to be made almost entirely out of dark matter, like up to 99% dark matter. They are incredibly heavy but almost invisible. But others, and this was a massive shock to the astrophysics community, seem to have absolutely zero dark matter. None at all.
Wait, if dark matter is this fundamental, ubiquitous particle that supposedly permeates the entire universe, how can a massive galaxy just have none of it?
Exactly. That is a huge headache for the standard particle theory of dark matter. If it is a physical particle, it should be everywhere. It shouldn't just decide to randomly skip certain galaxies. Why would one ghost galaxy be completely full of it and its neighbor be completely empty?
It doesn't make any sense. So how does constraint geometry step in and fix this?
Bhosale suggests a radical paradigm shift. He says dark matter isn't a particle at all. It's actually a phase of gravity.
A phase. Like how water can be a liquid or a solid block of ice.
That is the perfect analogy. Remember the aqueduct we just discussed? Remember the geometric Reynolds number?
Yeah.
Laminar flow versus turbulent flow.
Yes, the smooth, honey-like flow versus the chaotic, splashing flow.
Bhosale mathematically applies that exact fluid dynamic concept to the fabric of spacetime. He suggests that gravity itself fundamentally has two distinct operating modes. There's laminar gravity and there is turbulent gravity.
Whoa, gravity can get choppy, like a rough sea.
In the paper, he takes the Randall-Sundrum model and heavily modifies it. That's a famous model from 1999 that originally proposed a warp factor extending into a fifth dimension. It was trying to explain why gravity is so incredibly weak compared to the other fundamental forces, but in their original 1999 model, that warp factor was completely static. It was frozen.
And Bhosale basically unfreezes it.
Exactly. He makes it dynamic. He turns that static warp into what he calls a phase coherence field, which he mathematically labels alpha of x and t. He argues that the actual warp of spacetime can actively change based entirely on the local environment.
So gravity can flow incredibly smoothly, or it can get violently turbulent depending on where it is.
Yes. Now let's apply this new lens to those ultra-diffuse galaxies. If you look at the data, the ones that appear to have tons of dark matter are almost universally found in the deep, quiet, isolated parts of space. Void environments.
And quiet in this context means extremely low turbulence.
Exactly. In these vast, quiet zones, gravity is allowed to settle into its laminar phase. In this highly ordered phase, the geometric coupling is much stronger. The space-time warp factor stabilizes at a very specific mathematical value right around 0.35.
And when gravity gets stronger like that, it looks
exactly like what we call dark matter.
Yeah.
It naturally provides that crucial extra gravitational pull needed to hold a rapidly spinning galaxy together. You absolutely don't need to invent invisible exotic particles. You just need smooth, highly constrained space-time geometry. The inherent stiffness of laminar space holds the galaxy together.
Well, what about the ghost galaxies that have absolutely no dark matter? The ones that confused everyone?
Those are the ones located in highly turbulent environments. If a galaxy is sitting in a chaotic, bustling region, let's say it's falling inside a dense, massive cluster like a coma cluster, or it's recently violently interacted with another galaxy, the geometric phase completely collapses.
The solid ice basically melts back into chaotic water.
Yes. The rigid laminar phase is actively destroyed by the external environmental turbulence. The space goes turbulent. And when that happens, gravity just reverts to its standard, much weaker Newtonian form.
So the dark matter effect just evaporates.
It doesn't evaporate because it was never a physical substance to begin with. The underlying geometry simply changes phase. The extra grip of the laminar phase is lost to the chaos.
And that perfectly explains the split in the data, the bifurcation.
It explains the observational data flawlessly without ever invoking a single new theoretical particle. It directly connects the behavioral physics of a 17th century water aqueduct to the macrostatic behavior of a galaxy millions of light years away. It is all fundamentally about the geometric Reynolds number of the galaxy's local neighborhood.
This implies a universe where gravity isn't just a fixed, dumb constant. It's highly responsive. It reacts directly to its environment.
Which, as you can imagine, is a massive paradigm shift for physics. It means we've spent decades interpreting a geometric texture of space as a literal substance floating in space.
We mistook the shape of the waves for the water itself, or rather, we saw the water moving strangely and just immediately assumed there must be invisible heavy rocks pushing it around, when really it was just the natural dynamics of the flow itself.
That is exactly right.
This sounds incredibly promising. It's a very clean solution.
Right.
But I want to connect this back to the other big force we mentioned earlier. We spent a lot of time on gravity, but in the first section we talked heavily about the fine structure constant, which dictates electromagnetism.
Yes.
Section 4 of our outline is titled The Grand Unification. How do these two wildly different things actually connect? Because right now we have one number for laminar gravity, which you said is around 0.35, and we have a totally different number for electromagnetism, which is 1 over 137.
Right.
They seem totally unrelated. One is a huge macro scale thing, and the other is a tiny quantum thing.
They absolutely look different on the surface, but the source paper, titled Dual Projection of the Constraint Geometry Kernel, vigorously argues that they're actually mathematical siblings. They are simply dual projections of the exact same five-dimensional object.
We're back to the kernel again.
We are back to the kernel. I want you to visualize this complex five-dimensional geometric shape. It's highly structured. It's perfectly symmetrical. Now imagine you are shining a bright light on it from two totally different angles.
Okay, picturing it. Shadows on the wall. Very Plato's cave.
Exactly. Plato's cave is a great way to think about it. When you look at the extreme boundaries of this 5D shape, the very edges where it rubs against our flat four-dimensional reality, you see a certain amount of geometric leakage. You literally see structural information escaping the boundary. That specific leakage, that is what we experience as electromagnetism.
Electromagnetism is just geometric leakage. That sounds almost, I don't know, diminishing for such an important force.
Not at all. It's strictly defined as boundary leakage. In this grand theory, the fine structure constant, that famous 1 over 137, simply measures the mathematical efficiency of that leakage. It's a very small fraction because the boundaries are incredibly tight. It represents the tiny, necessary imperfection of the system at its very edge.
And what about the other shadow on the wall?
When you look away from the boundary and look at the bulk, the deep inside of the shape, and you measure how well it manages to hold itself together when you forcibly squash it from 5 dimensions down to our 4 dimensions, you see coherence. You see how well the core geometry retains its fundamental structure under dimensional reduction. That coherence is gravity.
And that coherence measurement is the 0.35 number.
Yes, that is the gravitational coherence parameter. So gravity and electromagnetism aren't two completely different physical forces that we have to artificially glue together with complex math. They are literally just two different ways of measuring the exact same geometric object.
So one number measures how it leaks at the edge, and one number measures how it holds together in the middle.
Correct. And this solves one of the biggest outstanding mysteries in physics, which is known as the hierarchy problem. The question of why gravity is so incredibly much weaker than electromagnetism.
Yeah, I remember learning about that. A tiny fridge magnet can pick up a paperclip and defeat the entire gravitational pull of the entire Earth. Gravity is notoriously wimpy.
Right. In this unified theory, gravity only appears weak to us here on Earth because we live in a highly turbulent phase where we're only seeing a tiny fraction of the true coherence. But in the deep laminar phase, the dark matter zones, it gets much stronger, hitting that 0.35 mark. And electromagnetism is naturally weak at 1 over 137 because it's fundamentally just boundary leakage. The specific numbers relate entirely to the geometry of the dimensional projection.
That is just incredibly elegant. I mean, whether it ultimately turns out to be true or not is obviously for the lab experiments to decide, but conceptually, it's truly beautiful. It neatly unifies the major forces into pure geometry.
And it completely reinterprets that old Randall-Sundrum warp factor. It's not just a clever math trick to balance an equation anymore. It's a physical coherence projection.
If this is all true, the entire universe is basically just one big, incredibly complex geometric shape. And everything we experience as physical forces are just the natural consequences of how that 5D shape projects its shadows into our 4D reality.
That is the absolute core philosophy of constraint geometry. Physical structure emerges exclusively from geometric constraint.
But there's one more massive piece of the puzzle here, and it's a big one. It's the one that really sounds like a wild sci-fi plot point. The paper titled The Structural Necessity of Attractive Gravity.
Yes. Section 5. The reality check, as we called it.
Because in science fiction, we absolutely love the idea of anti-gravity. We love the idea of just flipping a technological switch and making things suddenly repel each other. We all want floating hoverboards. But Palel explicitly says in this paper, no, you physically cannot do that.
He forcefully argues that the sign of gravity, the big G in the equations, isn't just an arbitrary setting on the universe's dashboard that happens to be positive. He mathematically proves that if you forcibly made it negative, if gravity were truly repulsive, reality itself would instantly break.
Break how? Exactly. Like things would just start floating away from each other.
Way worse than that, much worse. The paper heavily relies on something called the Ricciotto equation.
Bless you.
I know it's quite a mouthful,
Yeah.
but it is a foundational standard equation in general relativity. It essentially governed how bundles of light or matter mathematically focus or spread out as they move forward through time.
And focusing in this context means gravity pulling things together.
Right. Attractive positive gravity naturally focuses geodesics, which are basically the straightest possible paths through curved space. It allows these world lines to bundle up. It allows physical matter to clump together to form stars, planets, atoms. It brings things together.
And if gravity were somehow repulsive,
You get a state of global geodesic defocusing. Everything forcibly spreads out, always, everywhere, without exception.
so no stars could form, no
Yeah.
planets.
No atoms could form. The paper actively calls repulsive gravity the universal solvent.
The universal solvent. That sounds incredibly ominous.
It is a dark concept.
Yeah.
If gravity were fundamentally repulsive, it would ruthlessly tear apart any bound states. Even the strong nuclear force might not be powerful enough to overcome the underlying geometric tendency of space itself to rip things apart. There would be absolutely no orbits. Time evolution itself becomes mathematically incoherent,
Meaning what exactly? We wouldn't have a past or a future?
meaning you simply cannot mathematically describe a physical system evolving from state A to state B, because state A would instantaneously dissolve the moment it existed. It leads directly to what he calls thermodynamic death instantly.
So the core argument is that attractive gravity is a strict consistency condition. It literally must attract in order for complex observers like us to even exist to measure it.
And it's much deeper than just the standard anthropic principle. The idea that we are here, so the universe must be fine-tuned for us. It's a mathematical imperative. The mathematics requires this specific sign for a stable solution to even exist. If gravity were repulsive, the geometry simply couldn't close. You wouldn't have that 5D kernel we talked about earlier. You wouldn't have any constraints. The entire cosmic sculpting process would fail. The block of marble would just spontaneously crumble into fine dust before the sculptor could even pick up the chisel.
So the very fact that I'm sitting here in this chair right now being securely pulled down by the Earth is a direct, unavoidable consequence of the universe's desperate need to remain mathematically consistent.
Exactly. Gravity is the essential glue that keeps the geometry from dissolving into pure chaos. It is the ultimate constraint that allows any physical structure to exist at all.
This is a lot to take in for one session.
It really is. It's a complete fundamental rewriting of reality from the ground up.
Let's try to synthesize all of this for the listener. We started with the radical idea that the universe acts like a sculptor, constantly chipping away the impossible configurations.
The selection principle.
Right. And then we saw that this exact principle actually works in the real physical world, specifically in a 400-year-old Indian aqueduct that brilliantly uses strict geometric constraints to keep its water flow laminar and hyper-efficient without pumps.
The Nahar-e-Ambari.
And then we scaled that historical lesson all the way up to the cosmos. We learned that the mystery of dark matter might actually just be laminar gravity, a specific phase of spacetime that acts like a rigid structural support for galaxies, but only when the local environment is quiet and undisturbed.
Phase-governed gravity.
Next, we saw how gravity and electromagnetism aren't enemies or strangers, but are actually just two different shadows of the exact same 5D shape projecting into our world.
The dual projection.
And finally, we learned that gravity absolutely has to pull because pushing would literally unravel the mathematical fabric of reality and dissolve everything.
The structural necessity.
It's an incredibly complete package. It deeply connects history, civil engineering, high-energy astrophysics, and pure philosophy. But, and I have to play the skeptic here again because that's my job, is it actually true?
That is obviously the ultimate question. A scientific theory can be mathematically beautiful and still be completely wrong. The history of science is absolutely littered with gorgeous, elegant, wrong theories.
So how do we find out for sure?
This is exactly why I deeply respect Bhosale's work here. He doesn't just ask us to blindly believe his math. He actively gives us the Amber engine.
The tabletop test.
If you build that specific torsion pendulum and you precisely measure the energy efficiency, the theory makes a hard, specific prediction. It mathematically predicts a transient efficiency gain between 10 and 30% strictly due to configurational energy recovery.
And if you run the machine and the efficiency gain is 0%.
The theory completely fails.
And what if the efficiency is somehow 100%?
Then he's somehow broken the ironclad laws of thermodynamics, Or more likely his measurement apparatus is faulty, and again the theory fails. He has deliberately set hard falsifiable criteria. If the measured efficiency is less than 5% or greater than 100%, the theory is definitively dead.
That is incredibly brave. Most modern theorists hide behind excuses like, well, we need a particle collider the size of Jupiter to test this, or it only happens inside the event horizon of a black hole.
Exactly. He's putting his entire framework right on the table. Literally, he's essentially saying, build this relatively simple box in your lab, and if it doesn't work exactly as I predict, I am wrong.
So taking all of this in, what does this mean for, the average person, the listener driving to work right now or washing their dishes?
I genuinely think it changes how you look at the everyday world around you. You stop seeing empty space as just empty. You start seeing a hidden, rigid structure everywhere.
Yeah.
You realize that the mundane stability of your life, the simple fact that your car holds together on the highway, that the sun reliably rises, is the direct result of a constant, silent, cosmic process of geometric projection. The universe is actively, forcefully saying no to chaos every single microsecond of every day.
And that actually leads me to a really provocative thought based on the galaxies. If laminar gravity, the strong kind that holds massive galaxies together, requires a perfectly quiet environment, does that inherently mean stable civilizations can only physically exist in the deeply quiet, undisturbed parts of the universe?
That is a genuinely chilling thought to ponder. If your solar system was located in a highly turbulent part of the cosmos, like deep inside a dense colliding cluster or a violent galactic merger, would the local gravity itself become too choppy, too Newtonian to support long-term complex life? Does the phase of gravity essentially dictate the habitability of space itself?
Are we just incredibly lucky to be sitting in a perfectly laminar cul-de-sac of the Milky Way?
Maybe we are. Maybe peace and quiet isn't just a nice lifestyle choice. Maybe it's a strict physical geometric requirement for existence.
And on that heavy note, I think we'll leave you to ponder the complex geometry of your own reality for a while.
Indeed.
If you want to dive deeper into all this, and I highly recommend that you do, you need to check out the original source papers by Shrikant Bhosale over at twistpool.com. Look for the Feynman editions if you want a more accessible, heavily explained version, or just grab the full technical papers if you really want to sit down and crunch the tensors yourself.
And definitely keep an eye out in the news for anyone successfully building an Amber engine in their university lab.
Absolutely. Until next time, keep your constraints laminar.
And we'll see you in the next deep dive.
Before we fully wrap up, I actually wanted to ask you one more quick thing about the aqueduct because it really stuck in my head.
Oh, yeah. The Nahar-e-Ambari.
Yeah. The whole idea that a 17th century civil engineer was basically doing applied relativity without even knowing it, it really makes me wonder what other incredible physics secrets are just hiding in plain sight in ancient tech.
It's a really great point to bring up. We have this terrible habit of viewing the deep past as primitive. But Nahar-e-Ambari wasn't just blindly digging ditches in the dirt. The paper specifically describes those abgurnali, the vertical access shafts, not just as simple holes for pulling out buckets of water, but as crucial pressure relief valves for the geometric flow. He was actively managing the fundamental topology of the water network.
Topology, that's essentially the mathematical study of shapes, right?
Right. And you have to remember, water is a fluid. And space-time is, well, in this specific framework, it acts exactly like a fluid. The paper on phase-governed gravity explicitly refers to the shift as a hydrodynamic phase transition. So studying how water flows in a pipe is quite literally studying how gravity works if you are looking at it through this specific lens of geometry.
So when you and I stand on a bridge and watch a river flowing beneath us, and we see those really smooth, glassy sections right next to the violently splashing whitewater rapids,
You are looking at a perfect visual metaphor for the macro structure of the entire universe. The smooth, glassy water is the dark matter halo. It's coherent, it's strong, it's laminar. And the chaotic whitewater splashing over the rocks is the Newtonian chaos. It's turbulent standard gravity.
that visual is definitely going to stay with me for a long time. The universe as a giant river.
It's an incredibly old philosophical idea. Heraclitus famously said, "No man ever steps in the same river twice." But Bhosale mathematically adds a caveat to that. He says, unless the geometric constraints are perfectly constant.
Ishay, unless the kernel is closed.
Exactly. The kernel is the unmoving rock in the river that forces the water to shape around it.
Speaking of that kernel, let's quickly circle back to that specific number 1/137, the fine structure constant. You mentioned earlier that it measures leakage.
Yes, boundary leakage.
Does that phrasing specifically imply there are other places for that structural information to leak out to? I mean, if it leaks out of our specific 4D projection, where exactly does it go?
Well, now you're asking the really dangerous theoretical questions. The paper defines it as leakage at the boundary of the modular kernel. In a pure five-dimensional geometric structure, the word boundary could literally mean the extreme edge of our specific 4D slice of reality.
So electromagnetism, literal light, is basically just the excess stuff that's constantly trying to escape our dimension.
Or you could view it as the unavoidable friction of our 4D dimension, violently rubbing against the bulk of the fifth dimension. The leakage essentially prevents the entire system from being perfectly tightly closed. Think about it. If the fine structure constant were exactly zero, we would be trapped in a perfectly sealed box.
Yeah.
Absolutely no light would ever interact with anything. But precisely because it's 1 over 137, we have rich chemistry, we have complex interaction, we have light.
So imperfection is strictly necessary for life to exist.
Perfect modularity would be a completely dead universe. A perfectly closed, unyielding system has absolutely no interesting internal dynamics. You fundamentally need a little bit of leakage, you need a tiny bit of error in the math. That's exactly what the selection principle allows for. It drives the error down as low as possible, but it physically cannot eliminate it entirely without destroying the structure.
It aggressively minimizes the illegal intersections, but leaves just barely enough wiggle room for, well, for us.
Precisely. The information scaling law that's mentioned right in the title implies that as you scale up from the quantum to the cosmic, that tiny baseline information leakage defines all the macroscopic constants. It's a very holographic way of approaching reality.
Holographic in what sense?
The standard holographic principle in physics suggests that all the information contained inside a 3D volume is perfectly stored on its 2D boundary. Here, Bhosale is arguing that the fundamental constants of the bulk volume are entirely determined by the specific rate of leakage at the geometric boundary.
Man, it really does all connect together perfectly, doesn't it?
It certainly tries to. That's the grand ambition of any unified framework. Most modern string theories try to mathematically glue completely disparate things together with extra dimensions. This one simply tries to logically show they were literally never separate things to begin with.
I want to pivot back to the Amber engine one last time, because I just know some of our listeners are active makers, engineers, garage tinkerers. If someone actually wanted to try and build this thing, what does it physically look like on a workbench?
The schematic in the paper describes a highly sensitive torsion pendulum. So just imagine a very thin wire hanging straight down with a specific weight attached to the bottom. And that weight just freely twists back and forth on the wire's axis. That's your basic pendulum.
You're simple enough to build.
But the absolute key is the helical cage. Surrounding this twisting pendulum, you have to construct a rigid, perfectly machined structure shaped exactly like a helix, like a hollowed-out corkscrew.
And the pendulum occasionally hits the inside of this cage.
No. That's the entire trick to the device. It must absolutely never touch the cage. It relies 100% on clearance. Remember that geometric Reynolds number again? The clearance is the tiny physical gap between the violently moving pendulum and the completely static cage.
So it's basically a continuous near miss.
It's a perfectly calibrated near-miss interaction. The core theory mathematically suggests that the strict constraint itself, just the mere physical presence of that rigid boundary so close to the moving mass, actively affects the local energy state of the pendulum. It literally forces the local vacuum system into that laminar mode where the configurational energy can be naturally recovered instead of lost to heat.
That just sounds like straight up magic. I'm not physically touching you, but I'm somehow magically giving you extra energy.
It definitely sounds like magic at first, but think about the aqueduct again. The flowing water isn't physically touching the stone ceiling of the tunnel, but the overall shape of the tunnel absolutely dictates the flow of the water. The physical boundary condition completely controls the bulk behavior.
Okay, yeah, that makes a lot of sense when you put it that way. The boundary dictates the flow. So the helical cage creates a strict boundary condition for the local space-time and energy field immediately around the pendulum.
Exactly. And if you perfectly tune the swinging frequency of the pendulum to exactly match the physical geometry of the cage, that's the transition length variable, you hit a state of resonance. You hit the exact laminar sweet spot.
And that's exactly where you supposedly measure the 10 to 30% efficiency boost.
Hypothetically, yes.
Yeah.
That's the core testable claim. And the paper sternly warns experimentalists, if you get too greedy, if you push the Reynolds number too high above 10 by making the gap too tight or the swing too fast, the whole local field goes violently turbulent. The pendulum will start to wobble chaotically, the recovered energy will instantly dissipate as heat, and the entire macroscopic effect just vanishes.
So it's an incredibly delicate balance, just like Malik-Ambar's aqueduct.
Yeah.
If he had made the downward slope even slightly too steep,
The water would have rushed way too fast, gone completely turbulent, and violently eroded the stone tunnels from the inside out. The system would have literally destroyed itself in months.
but he got the math just right purely by intuition.
zero point 0.5 to 1.0 meters of drop per kilometer of distance. That was his exact slope. A tiny, gentle, almost imperceptible gradient. Just barely enough gravity to keep it flowing forward, but not quite enough to let it become chaotic.
That is just incredible precision for the year 1612.
It's civil engineering elevated to high art. And Bhosale is essentially saying the entire universe works the exact same way on a cosmic scale.
Yeah.
The fine structure, the gravitational constant, these aren't random numbers. They are the specific slopes that the universe slowly settled on to keep reality perfectly laminar, to keep all of us from violently eroding away into chaos.
I really love that concept. The universe is a masterpiece of ancient engineering.
It's an incredibly compelling worldview. Even if the tiny specifics of the high-level math turn out to need some minor adjustments in the future, the core philosophy that all structure fundamentally comes from constraints and not from invisible pushing forces is very intellectually powerful.
It really reminds me of that famous quote attributed to Michelangelo. I saw the angel trapped in the marble and carved until I set him free.
Exactly that. The trapped angel is the geometric kernel. The raw marble is the constraint geometry. And the act of carving is the selection principle.
So Shrikant Bhosale is basically trying to be the Michelangelo of modern theoretical physics.
Well, let's maybe wait for the Amber Engine Lab results to come back before we start handing out grand Renaissance titles. But the sheer ambition is certainly there.
Fair enough. But you really have to admire the massive scope of the project, spanning from mud brick aqueducts all the way to spinning ghost galaxies.
It's exactly what theoretical science should be. Highly interdisciplinary, completely fearless.
And most importantly, fun.
And fun. The pedagogical primer paper, the one titled, "So You Think You," Gravity's actually written in a surprisingly conversational, engaging style. It's not a dry textbook at all. It actively challenges the reader to play along. It literally says, turn the theoretical gravity knob to the left and see what happens to the math.
And what happens is the universal solvent destroys everything.
The immediate dissolving of all physical things. It's a really good physics story, honestly.
We should probably touch on that Raishaturi equation just a little bit more before we go. I know I glossed over it earlier, but it sounded incredibly important to the repulsive gravity argument.
It is absolutely fundamental to modern cosmology. It's the exact same equation that Stephen Hawking and Roger Penrose famously used to mathematically prove that singularities, things like the centers of black holes, are strictly inevitable under general relativity.
Okay, so we're talking absolute big league astrophysics stuff here.
Very big leagues. The core equation mathematically describes something called the expansion scalar, which is represented by the Greek letter theta. It basically tells you how the physical volume of a moving bundle of matter changes over time. The most critical term in that entire equation fundamentally involves gravity. If gravity is attractive, meaning it has positive energy, that specific mathematical term forces the expansion rate to decrease. Things are forced to focus.
Things are forced to come together and clump up.
Yes. But if gravity were somehow repulsive, meaning negative energy, that critical term would mathematically flip its sign. The expansion would forcefully accelerate. Geodesics, the actual physical paths of particles, would violently fan out in all directions.
Like a shotgun blast going off inside a tiny room.
Exactly, forever. And if paths strictly never converge, particles can literally never meet. And if they can't meet, they fundamentally can't bond. No chemical bonds can form. No nuclear bonds can hold.
So it's not just a macro problem of planets failing to orbit stars. It's a micro problem where basic protons wouldn't even stick to neutrons.
Correct. The strong nuclear force is incredibly powerful, and it actively holds the atomic nucleus together. But the underlying space-time geometry in which that force operates must be physically compatible. If the background canvas of space-time is aggressively defocusing everything, maintaining a tightly bound quantum state becomes energetically impossible. The energetic cost of holding anything together just skyrockets to infinity.
So the universal solvent isn't some literal chemical acid eating away at things. It's the background geometry of space itself, aggressively refusing to hold any coherent shape.
Precisely. It's the fabric of space fundamentally saying no to the existence of structure.
And attractive gravity is space saying yes.
Or at the very least, it's space saying, Okay, I'll allow this.
I'll allow it. That's a very bureaucratic way for the universe to operate.
Well, constraint geometry is essentially a highly bureaucratic theory of physics. It's entirely about strict rules, hard laws, illegal intersections. The universe acts as a very, very strict building inspector constantly checking the math.
And humanity is just the one weird building that somehow managed to pass code.
We are. Just barely passing code.
I wonder, though, if we look closely at those ultra-diffuse galaxies, again, the ghost ones with absolutely no dark matter, are they actively failing code?
In a way, yes, they are. They're deeply turbulent. They're completely failing to maintain the rigid laminar phase. And as a direct result of that failure, they are incredibly flimsy. They are easily torn apart by the gravitational tides of other passing galaxies. They are highly diffuse. They are ghostly. They entirely lack the strong structural integrity that the laminar dark matter phase naturally provides to healthy galaxies.
So they're exactly like the Indian aqueduct when the stern walls finally break. The laminar water just violently spills out everywhere and the system pressure completely drops to zero.
And the entire system immediately ceases to be useful. It ceases to be a singular, coherent object.
It's genuinely amazing how perfectly that one analogy holds up at literally every single scale we've looked at.
That's usually a very strong indicator of a fundamentally good theory, or at the very least a masterfully constructed one. When one single underlying mathematical principle, geometry-governed flow, can perfectly explain water in a pipe, swinging pendulums in a lab, and rotating ghost galaxies in deep space, you really have to sit up and pay close attention.
And that entire principle basically boils down to keep your re sub g as low as possible.
Keep it laminar. Always.
You know, I'm thinking about the listener at home again. We talked a lot about the falsifiability of the Amber engine. Is there anything big they can look out for in the astronomy news, aside from some guy building a weird pendulum in his garage?
Yes, absolutely. They should pay close attention to the new data coming from the James Webb Space Telescope.
Ah, JWST, our absolute favorite telescope.
Bhosale's paper specifically predicts that as JWST looks further back in cosmic time, or as it peers into vastly different galactic environments, we should mathematically see a very sharp, unnatural transition in galaxy behavior. We shouldn't see a smooth bell curve. We should see a hard phase transition.
A sudden jump in the data.
A massive jump. We should clearly see galaxies that are structurally turned on, meaning they are laminar and dark matter rich, and we should see galaxies that are completely turned off, meaning they are turbulent and dark matter poor. And that specific phase transition should perfectly mathematically correlate with the calculated turbulence of their local cosmic environment.
So if astronomers suddenly find a massive galaxy sitting alone in a perfectly quiet cosmic void, but it has absolutely no dark matter, that would be really bad for the theory.
It would be a catastrophic problem for the theory. The mathematics rigorously predicts that deeply quiet environments inherently induce the laminar phase. So a quiet, isolated galaxy absolutely should have a massive dark matter halo. If it doesn't, the entire geometric correlation breaks down.
And conversely, if they find a small galaxy getting violently ripped apart inside a chaotic, massive cluster, but it is somehow completely full of dark matter,
that would also be a massive problem. Severe environmental turbulence should instantly destroy the phase coherence. So the ongoing observational distribution of these UDGs is the ultimate cosmic testing ground for this entire framework.
So we basically have a highly controlled lab test with the Amber engine and a massive unscripted sky test with the UDG distribution.
Exactly. He is attacking the problem on two completely separate experimental fronts.
It's incredibly rare to get a new grand theory that actually offers both of those things right out of the gate. Usually, as we said, it's one or the other. It's either give me $1 trillion to build a collider the size of the moon, or let's just wait 1,000 years for a specific supernova to go off right next door.
That's the real beauty of the operationalizing part of his paper's title. Bhosale seems incredibly keen on making this theory highly workable and testable today, not a century from now.
Which kind of fits his unique profile perfectly. He's a researcher at a government medical college, heavily affiliated with a tech lab at Twistpool. He is definitely not your typical ivory tower theoretical physicist who just scribbles math on a blackboard all day.
And historically, sometimes, that's exactly where the biggest scientific breakthroughs actually come from the complete outsiders, from the brilliant people who can look at a crumbling stone aqueduct and somehow see the hidden structural mechanics of a spinning galaxy.
The ultimate cross-pollinators.
The great synthesizers of science.
Well, I certainly feel thoroughly synthesized today. My brain is definitely firing on some brand new geometric pathways after this conversation.
Just try to avoid making any illegal geometric intersections on your drive home tonight.
I will certainly do my best. I'll keep my car safely in the laminar lane.
Please do. We need you back here for the next one.
All right, well, this has been a truly incredible deep dive, going all the way from the dusty stones of Aurangabad up to the highly warped geometry of the fifth dimension. It's a very stark reminder that the universe is far stranger and perhaps far more beautifully engineered than we typically give it credit for.
And a reminder that it's all fundamentally connected at the deepest possible level.
It really is all connected. Thank you so much for patiently guiding us through the heavy math today.
It was my pleasure. It's always really fun to stretch these specific mental muscles.
And a huge thank you to Shrikant Bhosale for providing us with such an incredibly rich and detailed playground of fresh ideas to explore today. Once again, twistpool.com is the exact place to go if you want to verify everything we just discussed, or if you want to try and prove us all wrong.
True science always welcomes a rigorous challenge.
That it certainly does. Thanks for hanging in there and listening, everyone. We'll catch you on the next wave.
Or the next geodesic.
Or the next geodesic. Take care, everyone.